So my name is Amran Siddiqui. I'm talking on behalf of my colleague Shubhamay Dash. So I'll talk about incorporating feedback into tree-based anomaly detection. So let's first see what is anomaly detection with a very simple example. Suppose you are given this collection of lemons and asked to find which one is actually rare or unusual. So the problem here is pretty simple in this case. And you can see which one is the anomaly. But in real life, the anomaly you are interested may be something very difficult. For example, maybe it's a security attack in a computer system, where each object will be represented by a set of system behaviors. So now let's look when an anomaly detection system actually employed in practice, what actually happens. So we have an anomaly detection detector f of x, which means if we give an instance x, it gives us a score. And in here we are considering higher score means anomaly and lower score means nominal. So we can pass all the objects to this anomaly detector and we can get a ranking for all the objects here. Here the green objects represents normals and the red one represents anomaly. So what happens is usually a system analyst goes through this ranking from top to bottom, one by one. So the analyst look at the top of the instance and examine it further. And if he doesn't find anything interesting, he simply moves to the next object. And then he continue this process until a budget expires. So the problem with this typical approach is usually the anomaly detectors we use are a statistical anomaly detector. So they are very good detecting statistical anomalies, which might not correspond to a real anomaly. For example, in the computer system, there can be a lot of unusual behaviors, but not all of the behaviors actually will be a security attack. So the job of anomaly detector will be to differentiate between these two and detecting actual anomalies. So this causes a great problem that the analyst need to deal with a large number of false positives. So he might not be able to reach the actual anomaly, the red point here. So in this work, we are trying to help the analyst by incorporating feedback. So the idea is similar. So analyst goes through the list, but this time when he examines an instance, if it's anomaly or nominal, he provides the feedback to the anomaly detector. So the anomaly detector then adjusts itself. So we'll get a new ranking, and we expect the anomaly will be top in the ranking. So then he goes to the next instance, and he again provides feedbacks. This time it's also normal point, and the anomaly will rise, and the analyst will continue this way, and eventually reach to the anomaly point and give this feedback to the anomaly detector. And we'll get this point rank at the higher. So the benefit of this approach is it's actually adaptive, interactive. So analyst going through the list of the top instances and then giving feedback, and the anomaly detector is updating itself. And the major benefit is it reduces number of false positives. So there are lots of different types of anomaly detectors. And in this work, we mainly focus on tree-based anomaly detectors. Here is a couple of examples. And we want to incorporate feedback into this set of tree-based anomaly detectors. So to choose a representative anomaly detector, we are using here isolation forest because its performance is really good compared to the state-of-the-art other algorithms. So let's look how this isolation forest anomaly detector works. So the simple idea is it judges a point based on how easy to isolate a point from others. For example, if you can isolate a point from others very easily, it means that point is actually an anomaly. On the other hand, if it's hard to isolate a point from others, it's actually a normal point. So to do that, what isolation first does, it creates this randomized binary tree where each node represents a random feature test. And if we see a simple snapshot in 2 dimension, you can see here. So if you look into this region here, so here is a point, and you can see this point is in a region which is less crowded. So isolation first will draw random lines, either vertical or horizontal, in two-dimensional space to isolate this point. So it will be easier to isolate this point from rest of the points. So this point will actually live in the tree in a shallow leaf, which will indicate anomaly point. On the other hand, if we pick a point from in the center here, it will be hard to isolate. So the algorithm need to draw lots of lines, which means lots of pastes. So this point will actually go deep in the tree, and it will be a normal point. So here I'm showing a corresponding contour. So from the depth, we get some anomaly score. And here red region means anomaly, and the blue region means nominal, normal. So usually one tree in practice is not robust enough, so we have to use ensemble of many trees. As you can see to the right, the contour becomes much better. So we want to incorporate feedback to this algorithm. So to do that, we first have to convert this tree representation into a more useful form. So for that, we will represent here this tree as a weighted representation, as a linear form. So you can see in a decision tree, each node, for example, here x is traversing this specific red path, as you can see. So we are assigning binary features on each tree node. So if an instance go to that node, that feature is active. We are assigning corresponding value -1. So the z of x will be the feature representation for this x. And this new feature representation is actually really large, because this is actually total number of nodes in the entire collection of the trees. But the good news is this vector is really sparse. Maybe we have 1,000 nodes in this entire tree, but for one instance, only 10 nodes will be active, probably at most. Then we have to assign weights on each of the nodes. And for isolation, it's very trivial. If we just assign same weights, say 1 on all the nodes, it corresponds to exactly isolation first score. The thing to note here is, if we assign a different set of weights, it will correspond to a different tree-based anomaly detector. So we can incorporate feedback in the same way as for isolation forest. Then we can compute the score of a point, just the dot product of this two vector, feature and the weight. So when we want to incorporate feedback, so we just want to learn a weight that will also satisfy some constraints. So how we are incorporating that feedback, now I'll describe in here. So the algorithm we are calling that takes feedback is active anomaly discovery. So the basic idea is, what we care about is accuracy at the top, which means we only care about, say, top 10 or 20 instances, because in reality, an analyst will only look at that region. So the bottom region doesn't matter. So we want our anomalies to come at the top. So for that reason, to define a top, this algorithm has a parameter, tau, that's actually defines a quantile. So if you want your anomaly points to come, say, top 1% of the data, you assign tau equal 1% here. So the algorithm will try to put anomalies at the top of this point and nominals below this threshold point. So suppose at time t of the iteration, we learned a weight wt, and we scored the instances based on that weight, and this is the ranking. And so far, suppose we got 2 feedback, those are true anomaly. So the algorithm put those above the threshold line. You can see 2 red points. And suppose it received 3 normal points, so it will put the points below that threshold. And the analyst will always going to look at the top instance that haven't received feedback. So analyst will look at the top here, and he will examine the instance. Suppose he finds that this instance is actually a normal point. So now this algorithm will try to put this top instance below the threshold. So to do that, the algorithm will actually learn a new weight. It will infer new weight wt plus 1. So it will just not put the instance there. It will change the score of the nominal point so that it becomes now lower than the threshold we are choosing here. So this might change the ranking overall, but the constraint must be satisfied, which means the known anomalies will always be above this threshold and non-normalized will be below this threshold. Then analyst will continue this way. Now he'll again look at the top instance. Suppose this time we encounter a real anomaly. So this feedback will go to the anomaly detector. Because it's a real anomaly, you can see the constraints are already satisfied, so we don't necessarily need to change the weight. So the analyst will simply move to the next instance that haven't received feedback yet. And he'll give the feedback and anomaly detector will update. And this process will continue until a budget expires or a fixed number of iteration. So this is the idea of the taking feedback into anomaly detection. Now let's see what happens if we apply this feedback technique. So first we'll look into a very simple data set, so a two-dimensional synthetic data set. And you can see here there is only two regions, here and here. These two regions anomaly points are coming. And in the bottom left picture, you can see the baseline contour of the isolation forest scores that doesn't have any feedback. So in top 35 points in the ranking, it actually detects 12 anomaly points. And on the right side of the bottom, we can see what happens after feedback. So as you can see, if we give 35 feedbacks, then it actually detects 23 anomalies, much more than 12 anomalies. So how we actually go from this first step of this contour to the final after 35 iteration, let's see that sequentially. So this is the initial stage without feedback. So right after 10 feedback, you can see the algorithm is now more focusing on this region and also this region, because this two region, it already got feedback, there are anomalies. Then in 20 feedback, it's adjusting more. And after 25 feedback, it's still adjusting. And after 35 iteration, you can see it's kind of recognize that these two regions actually more important. It detects more anomalies. So this is the result on a two-dimensional data set. Now, if we see in more realistic data set and with high dimension, what exactly happens? So here we use two data sets, abalone and thyroid, and we used a tool called tsne that actually reducing the high dimensional space into 2D. So this is 2D representation of these two data sets. And you can see the markers, the green circles, those are actually indicating highly ranked points. And green means it's actually false positive. And red plus means those are true positive. And blue plus means those are anomaly, but we miss them. So they're actually false negative. So when we apply feedback, so this is actually the result after feedback. And what to look here is, you can see here, so here we got one anomaly feedback from the analyst. And you can see the corresponding region after feedback that the algorithm is focusing in that region more. It means it is detecting even more anomalies. The same goes in this data set also. Here it detected a couple of anomaly points, and it more focuses on that region, so it detects even more. And another interesting thing is, you can see here a cluster of false positives. But when we give feedback, you can see in this region, right after just one feedback, the algorithm shifted focus from somewhere else. It means this point is normal, and there is no other point ranking top from that region. So this is the overall result. On x-axis, we are showing a number of feedback iteration, and y-axis, we are showing how many anomalies the analyst found so far. And we compared this feedback approach to isolation forest with a baseline, the blue curve that doesn't have any feedback, and a green curve, similar different anomaly detection, LODA. And we found in general the feedback on isolation forest actually perform better than other techniques. As you can see in different data sets, the red curves is performing much better than others. So in conclusion, we want to say that human feedback is actually essential in certain applications. And the major benefit is it improves the unsupervised learner. And this is an ongoing work, so we want to extend this to other different anomaly detectors and also want to improve better optimization techniques. And we are especially interested in explanation-based feedback, which means that for some domain, it might be very hard to give feedback that this is exactly anomaly or this is nominal, or it might be very costly. But instead, if we show an explanation, which means if we show the reason why the anomaly detector thinks this is an anomaly, then the human analyst can say, okay, this might be a very important reason, so show me more instances like this, or this might be just a benign reason, you can just ignore it. And that's all. Questions?